Ooh. Ooh. Boo! Okay. Hey there, guys. My name is Charles. And today I'll be presenting about the Spectre attacks, exploiting speculative execution by all of these authors. So, uh, what is a Spectre attack? So, Spectre attacks are attacks that exploit speculative execution, which is a performance enhancing feature in modern processors to extract data from a victim. So why is it called a Spectre attack? Because speculative executions execute instructions that weren't supposed to be executed and then revert the changes, as if they have never happened, except changes have been made and we can see traces of the changes. Similar to how a ghost would haunt a house, things move, etc. Why is this important? Well, this vulnerability is a big deal because it affects billions of devices, or it affects processors that are in billions of devices, or at least were. Right, this happened back in 2018, I believe. So to understand the attack, we have to first talk about modern processor design. So modern processors were designed with uh, performance prioritized over security. Uh, this so several key features of processors include the out of order execution engine, the branch predictor, and the execution unit. So the out of order execution engine is a design paradigm in modern CPUs for improving performance. The CPU tries to maximize its utilization by executing instructions in an order different from the program's original sequence. So instead of waiting for a preceding instruction to finish, the CPU can start executing following instructions that are independent of the pending one. In this example, if C and D aren't ready yet, the out of order execution engine will go ahead and see if it can execute this instruction in order to not be idle. As part of the out of order execution, modern CPUs break down complex instructions into smaller micro operations. For example, an instruction like add A, B, C, which translates to add B and C and load it into A, will be broken down into these smaller instructions. As a result, this makes execution easier to manage and allows for parallelism. So next, the reorder buffer. After executing instructions out of order, the processor must ensure the program's state remains consistent. This is done using a process called instruction retirement, where instructions are organized in order for the program, or are organized in order for the program. This ensures that the results align with what the program expects. To help with this, the reorder buffer tracks which instructions have executed but not yet retired, and once an instruction has been fully executed and all preceding instructions have been completed, the instruction is committed. Think of ordering a burger at a restaurant. The chefs get an order ticket detailing what the customer wants. It doesn't really matter what part of the burger is ready first. The burger will be delivered to the customer when it's complete. So a chef can be grilling patties while another is slicing the tomatoes, for example. In the end, as long as the chefs put together the burger that the customer wanted, they did their job, and the order ticket can be discarded to make space for the next order. Sometimes the processor would not know what the next instruction should be. For example, when encountering a conditional branch instruction, where the next step depends on the conditional statement, where the preceding instructions are incomplete, but the processor doesn't want to stay idle. It was made to be efficient. So in this case, the processor will save state, guess the path that the program will follow, and perform a series of speculative executions along that path. Here we have the out-of-order execution engine, the execution unit, and the branch predictor. The out-of-order execution engine performs the speculative executions. The branch predictor predicts the outcome of the conditional branch, and the execution unit verifies the branch predictor's guess. So the out-of-order execution engine starts executing instructions based on the prediction of the branch predictor. So go right, okay, go right. A few clock cycles later. In this scenario, the branch predictor was correct, which it usually is. The prediction is verified by the execution unit, and the progress already made by the out-of-order execution engine is committed, enhancing performance. However, in this scenario, the branch predictor guesses wrong, and the out-of-order execution engine reverts any work it has done by reverting the register state and resumes along the correct path. So these speculative executed instructions that were performed mistakenly are called transient instructions. These transient instructions may leave microarchitectural traces, things like cache access times, delays in execution, varying power consumption, etc., which can be exploited in attacks like Spectre, leaking sensitive data through microarchitectural covert channels like CPU cache. And brief review. A microarchitecture refers to the CPU's internal design that determines how instructions execute, how data flows, and how performance is optimized. And microarchitectural traces are the residual effects that computations leave on a CPU's microarchitectural components. So, for example, these traces would be stuff like delays in execution and varying power consumption that is noticeable. Okay, so now let's talk a bit about memory hierarchy. Accessing data from RAM is much slower than accessing data from a cache. So the processor caches frequently accessed memory. And processors have a hierarchy of caches. L1 and L2 caches are dedicated to each core, while the L3 or last level cache is shared among the cores. So L1 and L2 caches can be exploited if the victim and attacker share a core, and L3 can be exploited if the victim and attacker share a processor. Instead of fetching individual bytes, the cache fetches and stores an entire line of data, called a cache line, because of the principle of spatial locality, which says that if one memory address is accessed, nearby addresses are likely to be accessed soon. These cache lines act as a covert channel to leak data. Since the changes made to the cache are not reverted, the cache lines brought into the cache during speculative execution remain there. Cache hit occurs when the CPU requests data and the data is already stored in the cache. It is a lot faster because the cache is closer to the CPU than main memory, as we went over in the previous slide. A cache miss occurs when the data requested is not in the cache and the CPU has to fetch it from the main memory, which is slower. Attackers can take advantage of this microarchitectural trace, that is the timing difference, to extract information. In this paper, authors used the flush plus reload and evict plus reload techniques to leak sensitive information. In these methods, the attacker begins by evicting a cache line from the cache that is shared with the victim. After the victim executes their process for a while, the attacker measures the time it takes to perform a memory read at the address corresponding to the evicted cache line. If the victim accesses the monitored cache line, the data will be in the cache and the access will be fast, thereby informing the attacker that the victim accessed the monitored cache line. The attacker can repeat this process multiple times to infer the secret value. The difference between the two techniques is the way they evict the monitored cache line from the cache. In flush plus reload, the attacker uses a machine instruction like x86's CL flush to flush the specific cache line out of the cache. Using evict plus reload, the attacker forces the cache to remove specific data by filling the cache up with other data. This way they can see that the data was accessed if the data reappears in the cache. Spectre attacks typically involve three main phases. First, the setup phase. The attacker mistrains the processor by inducing branch mispredictions or manipulating indirect branch targets. Techniques like flush plus reload are used to prepare the covert channel, which is a method used to transfer information in a way that is unintended by altering the cache state. The next step would be the speculative execution phase, where the victim process is triggered to speculatively execute instructions that would not normally run in strictly in-order execution. This speculative execution leaks sensitive data, such as reading a memory value at an attacker-chosen address, then performs a memory operation that modifies the cache state in a way that exposes the value. And lastly, we have the data recovery phase, where the attacker recovers the leaked information by measuring timing differences in memory accesses, for example, via cache timing techniques. So variant 1, exploiting conditional branches. In this variant of the attack, consider the conditional branch example, where the code is part of a function, like a system call, receiving variable x from an external source. For this example, we assume that array 1 size and array 2 are not cached, and that array 1 at x or k is cached. This is to allow for the processor to speculatively execute the inside instruction while the execution unit figures out whether or not the conditional statement is true. So, if these variables are not cached, it takes longer for the CPU to determine their value, as it has to get the value from memory, which is slower. So that's why we make these assumptions. Without the bounds check, an out of bounds x could trigger an exception or could cause the processor to access sensitive memory by supplying x with an address of a secret byte to read, subtracted by the base address of array 1. The attack works by first attacker mistrains the branch predictor by repeatedly running the code with valid x values so that the processor learns to predict that the conditional branch is usually true. Then the attacker provides a malicious value for x such that it is out of bounds, and array 1 resolves to a secret byte k somewhere in the victim's memory. Due to branch prediction, the CPU speculatively executes the next line before verifying the conditional statement. The speculative execution reads a secret value k from some memory address. The secret value k is used to index array 2 at k times 4096, storing it in the cache. The processor realizes the mistake and discards the speculative execution, but the cache state remains changed. The attacker measures which address in array 2 was cached using cache timing attacks like flush plus reload. Whoa, why did it turn dark? What the heck? Okay, since k determines which cache line was loaded, the attacker can infer the secret value. A proof of concept attack was implemented in C. If the compiled instructions in the victim function were executed in strict programming order, the function would only read from array 1 indexes 0 to 15, since the size is 16. However, when executed speculatively, out of bounds reads could occur and leak the secret stream. So let's break down the read memory byte function. The results variable stores access timing results for each possible byte 0 to 255. These variables are used for iteration. Training x and x are variables used to control speculative execution training. Time 1 and time 2 are used to store timing info for cache accesses. And this pointer is used to probe addresses in the cache. And this for loop here just resets the results, all values in results array to 0. And this for loop here makes sure that the attack is repeatedly performed for accuracy. And this for loop here flushes the cache or array 2 values from the cache before the attack. Since the attack relies on cache access timing to determine which entry was accessed, we flush the cache for a clean state. Training x is set as a valid array index within array 1, and the next for loop performs 30 iterations where 1 in every 6 iteration would be a malicious value for x, and the other 5 would be using the trailing value for x. This command flushes array 1 size from the cache to force the processor to fetch it from RAM, which is slower than fetching it from the cache, ensuring that speculative execution can take place. This loop is to put in a delay to make sure that the cache is properly flushed before proceeding. This bit twiddling part is just to carefully set the x to the training x most of the time, but to a malicious value of x every 6th iteration. So lastly, the victim function gets called, and in short, the function makes several training calls to the victim function to make the branch predictor expect valid values for x, then calls with an out of bounds x. the conditional branch mispredicts, and the ensuing speculative execution reads a secret byte using the out of bounds X. The speculative code then reads from array 2 at array 1 at X times 512, leaking the value of array 1 at X into the cache state. So Spectre attacks can recover data with high accuracy, but errors can still occur due to timing, measurement, and accuracy. Furthermore, unexpected caching from hardware prefetching, operating system activities, or other processes accessing the same target memory can also cause errors. So the attacker can simply repeat the attack multiple times to improve the accuracy. In variant 2, the attack involves training the branch target buffer, which keeps the mapping from addresses of recently executed branch instructions to their destination addresses to mispredict and misdirect an indirect branch instruction outcome to the address of some attacker-chosen code called gadgets. In other words, the attacker mistrains the branch predictor with malicious destinations such that speculative execution continues at a location of the attacker's choosing, typically leading to the exfiltration of sensitive data. As shown in the figure in the slide, the branch predictor is mistrained in one context and applies the prediction in a different context, speculatively executing the gadgets rather than the intended function. These gadgets read sensitive data and exfiltrate it via covert channels like cache states. This is particularly dangerous because the attacker can misdirect speculative execution to locations that would never occur during legitimate program execution. So in this attack, an attacker seeks to read a victim's memory by exploiting indirect branch prediction. This assumes that the attacker has control over, meaning that it provides value for two registers, R1 and R2. The attack requires a Spectre gadget, we explained earlier, in which it's a segment of the victim's normal code that, when executed speculatively, could use those registers to leak sensitive information. So the attacker mistrains the branch predictor by repeatedly executing a specific pattern that convinces the processor to predict that an indirect branch should jump to the Spectre gadget instead of its intended target. The CPU speculatively executes the gadget before realizing the branch was mispredicted. And register 1 points to a secret value in the victim's memory. The gadget loads the secret value from R1 into R2, and then the gadget uses R2 to access memory, which alters the CPU cache state in a way that depends on the secret value. So even though the CPU discards the speculative execution, the cache state remains changed. The attacker can measure the memory access time using flush plus reload to determine which memory location was accessed, and from there they can infer a secret value, R2. The authors tested Spectre attacks on various processors and found that the following processors, at least, were all vulnerable to Spectre. These findings also indicate that Spectre affects both 32-bit and 64-bit modes across Linux and Windows operating systems and even kernel-based virtual machines. In order to help with the design and evaluation of mitigation techniques, the authors explore alternate methods that attackers could try to perform Spectre attacks, showcasing the variety and combinations in which the attack can be carried out. Examples include the vict plus time attack, where the attacker measures execution times differences based on whether a speculative memory access hits or miss in the cache. So even if the CPU prevents speculative cache writes, timing effects still reveal data. Even without conditional statements, an attacker can mistrain branch predictors and use interrupt misprediction to force speculative execution of a secret dependent instruction. Even if speculative execution doesn't modify the cache state, it still influences CPU timing, bus contention, power usage, or even magnetic signals. And an attacker can manipulate these effects to create a covert channel for data leaks. So the key point here is that Spectre doesn't rely on cache side channels only. The problem stems from a fundamental CPU design feature where any observable effect of speculative execution can potentially be used to leak information. The authors review some of the proposed mitigation strategies and evaluate their applicability, effectiveness, and cost. So, since speculative execution is required for Spectre attacks, one may ask, why not just disable it? Well, the costs of disabling speculative execution would be performance, as speculative execution has been shown to significantly boost processor performance. Furthermore, current processors have no software method to disable the feature, but such modes could be added in future processors. Other suggestions include switching to alternate processors that do not implement speculative execution, but this solution is unlikely to provide an immediate fix to the problem. Alternatively, software could be used to use serializing speculation blocking instructions to ensure that instructions following them are not executed speculatively. Intel and AMD recommend using the lfence command, which is used to prevent speculative execution beyond a certain point. This could be inserted after every conditional branch, but this is inefficient and slows performance. A more optimized approach would be to use software analysis to selectively apply speculation blocking where needed. Another proposed method is to disallow speculative execution from accessing sensitive data in the first place. For example, Google Chrome implemented site isolation where each website runs in a separate process, so a Spectre attack in one site cannot access memory of another site. Even if speculative execution occurs, the attack only works if secret data enters a covert channel like cache state changes. No current processors have this capability, but future processors can track whether data was fetched via speculative execution and prevent it from being used later. To exfiltrate information from transient instructions, Spectre attacks use a covert communication channel. Suggestions have been made to mitigate such channels. For example, browsers degraded the resolution of performance.now, which is a timer in browsers with JavaScript, to make it harder to measure cache access times. However, these countermeasures only slow down the attack and do not completely prevent it. Branch prediction training, or rather mistraining, is a key Spectre technique. Intel and AMD introduced new CPU instructions to restrict indirect branch prediction. These mitigations require microcode updates and OS/BIOS support, and performance impact varies depending on how heavily they are, from small, which is like a few percentage slowdown, to severe, which is a 400% slowdown. Google suggests an alternative mechanism for preventing indirect branch poisoning called REPLines, which is a code sequence that replaces indirect branches with return instructions, and this prevents branch poisoning with minimal performance costs, does not require CPU modifications, and is already adopted in major OS updates. However, it may not work on all CPU architectures. A fundamental assumption underpinning software security techniques is that the processor will faithfully execute program instructions, including its safety checks. However, in this paper, the authors showed that with Spectre, that this is not always the case. So while the countermeasures proposed are good temporary fixes, there is no formal assurance that specific code is safe across all processors until processor designs are redesigned at the hardware level with consideration of both security and performance. Some acknowledgements. Firstly, the novelty of the attack. Unlike traditional side channel attacks that rely on software bugs or memory safety vulnerabilities, Spectre exploits a hardware design flaw in branch prediction and speculative execution, which is a feature that is normal and intended in CPUs. The paper challenges the assumption that safety checks in software are always enforced by the CPU before execution, and generalizes the attack across multiple architectures, showing that Intel, AMD, and ARM processors are all vulnerable. Also, Spectre gadgets. The paper introduces the concept of Spectre gadgets, which are existing sequences of legitimate instructions in victim code that can be hijacked through speculative execution. So attackers do not need to inject their own code, but instead redirect speculative execution into victim code. Also, the authors reverse engineered how CPUs store and use branch history to show how attackers can mistrain the branch predictor to manipulate speculative execution paths. They find that history-based predictors, such as those in Intel and AMD processors, allow attackers to influence future speculative execution even across different processes. This allows them to mislead the CPU into executing out-of-bounds memory accesses that leak sensitive data. The authors provide multiple proof of concept implementations to show that Spectre attacks are feasible in the real world. They implement Spectre attacks in C, JavaScript, and kernel exploitation. However, in this presentation, I only went over the C implementation. The attack works remotely in browsers, proving that just visiting a malicious website can expose private data. Lastly, Spectre attacks do not cause crashes or leave logs, making them stealthy, and this is also unique. The authors demonstrate multiple cache timing side channels to extract secret data from speculative execution, showing that the attack is not limited to just like one side channel. They also discuss how other microarchitectural effects, such as execution unit contention and power consumption, could also be exploited in future Spectre-like attacks, showing that the attack doesn't rely on one side effect. Some criticism. No fully remote exploit demonstrated. The paper does not provide a fully remote Spectre attack. The closest remote scenario in the paper is the JavaScript-based exploitation in browsers. The attack is shown to work on multiple CPUs, but not all architectures behave the same way. So some CPUs may not leak information in exactly the same way due to variations in speculative execution behavior. Most of the Spectre attacks rely on cache-based covert channels for exfiltrating data. However, the paper does acknowledge this and suggests alternative covert channels, including power analysis. The paper proposes some mitigations, but many of them are impractical or significantly impact performance. The authors do not provide a systematic security model for how to rethink speculative execution securely. The authors did not really suggest any new mitigations, just proposed mitigations by others and reviewed them. Lastly, the ethical considerations were not fully addressed. The disclosure timeline was complex, and CPU vendors had to rush mitigations without clear solutions. And the paper does not extensively discuss the responsible disclosure process or its potential impact on providers, operating system developers, and hardware manufacturers. That was all for my presentation. Thank you. Hopefully you learned something. Take care. Bye.